Hi, everybody. Welcome to the Force Seminar. Thanks for joining us today. I'm Kara Brugman, Research Science here at Force.
And QC Tsuno, also the research scientist for the force.
Today, we have a talk from Steve Greaux about elastic wave velocity measurements at high pressure and high temperature and its applications to the study of the Earth's interior. But first, I want to remind you, of course, that this meeting is being recorded and that it will be available on YouTube probably in 2 weeks. So do be sure to join our mailing list to get a notice of when that recording is available. You can also see a video of all of our previous seminars up on your YouTube channel. And you can follow us on our other social medias. You can see right here. We have one more seminar this semester by Felix Marxer from Leibniz University at Hanover. And if you would like to suggest a speaker for the Force seminar, including yourself, you can visit this link here, bit.ly/Force seminar suggest. Meanwhile, in lab news, this week we installed our final piece of equipment, the internally heated pressure vessel. And we also just started our training for the internally heated pressure vessel with Florian Pohl from Vili Geotechnik. It's been going really well. The IHPV is really an amazing piece of engineering, and we're excited to get used to it or start to use it and to welcome users once our implementation grant is over and we're open for business. And of course, I also want to remind you all that registration for our third winter workshop is open. You can go to bit.ly/force WW25reg to get the Zoom link for that. There's no cost for this because it's all virtual. We held the mornings of Tuesday, January 14th and January 15th. We'll have keynote talks from Dan Frost, Fabrice Gaillard, Tomo Katsura, and Megumi Kawasaki. All right, without further ado, I'll pass it over to Kisei.
Yeah, so we are very delighted to welcome Dr. Steve Greaux from the Ehime University's Geodynamic Research Center as today's speaker for the fourth seminar. So Dr. Greaux earned his PhD from the University of Paris East before joining Ehime University. Initially as a postdoc, he was hired as a postdoc and subsequently promoted to assistant professor, and later his position was secured as a tenured lecturer position. His research specializes in mineral physics, particularly utilizing large volume presses such as multi-anvil devices, often in conjunction with synchrotron X-rays. So today he will discuss the inhomogeneity of the Earth's mantle transition zone, drawing insights from the seismic velocity measurements. Okay, Steve, you can start.
Okay, thank you, Kyusei, for the introduction. So can I share my screen? Okay, can you see my slides? Okay, good.
Yes, yeah.
Okay, so thank you for having me today and giving me the opportunity to present this talk. So you can see the title. So today I want to talk about this elastic wave velocities, measurement of any materials, but particularly for those related to the Earth's interior, and show a little bit some progress that we made here at Ehime and show how this can be applied to get further information from the Earth's interior. So let's start. Okay. So as you know, the laboratory studies of the elastic wave velocities provide a unique tool that we have to investigate the interior of the Earth by a direct comparison of the information, the seismic global seismic model derived from the seismic wave from the earthquake. And that information, we can compare it directly to some elastic wave velocity measurements that can be done in the multi-anvil press, but also in the diamond orbit cell. So today, I'm particularly talking about the multi-anvil press and the ultrasonic interferometry technique. So this technique is by no means new. It has been used in many diverse ways in the past. If you want more history of this kind of measurement, I invite you to read this very interesting paper by Bao Sheng and Bob Lieberman. And but I will start from this point actually. So And I will start from this time. At this time, so it's at the time where the Baosheng implemented this ultrasonic interferometry technique to the multi-anvil press, which allowed to analyze to measure the sound velocities in the minerals under high pressure. So, as we know, so the global seismic models, such as the PREM and the AK-135, show very distinct features, particularly in the mantle transition zone, which is the mantle region that stands in between 410 kilometers and 660 kilometers. So this region appears to be a very complex layer, which is marked by velocity jumps at 410 and 660. And also high velocity gradient in the mantle transition zone. But also recently, some adjacent low seismic velocities, which are characterized by low seismic velocities, but also high attenuations. So several hypotheses have been proposed to explain the observed seismic anomalies, among them phase transitions associated with mantle temperature variations, such as proposed by recently the Katsola-Sans group, and mostly addressed to the 660. But also the effect of chemistry and mineralogy, which is something that we have particularly investigated at EHIME, where we propose that changing of the rock chemistry and the properties under pressure could explain those discontinuities. And also, more recently, there is some work that proposed the presence of partial melts at several depths, widespread around the globe, which could explain those low seismic, particularly those low seismic velocities. So in this presentation, I would like first to give an overview of the ultrasonic measurement at simultaneous high pressure and high temperature, how it is done, and what are the experimental requirements to carry out such measurement. Then I will show, by showing some previous work, how these techniques has been used so far to constrain the elasticity of mantle minerals. Then I will discuss the mineral physics model that derive from those studies relative to other geophysical studies. Then in the last part of my talk, I would like to present some of the current research we are doing now, which aims at reconciling some mineral physics data with seismic observations. And by doing those measurements on something like more natural, since something that looks more natural like rocks or partially molten rocks. So to start my talk, I would like to show a few pictures here. So probably some of you who have visited Springate, beamline BL4B1 are familiar with this environment. So this is the beamline 4B1 where we carry out those high pressure and high temperature experiment. And the experiment are generally carried out in this press, which is called speed 1500. It's a diatyped press with just the diatype press. It doesn't have deformation modus, but the advantage of having this configuration is that we can take advantage of a large aperture to and have a relatively larger view of the sample by the X-ray radiography. So here I just show a picture of the cell, which is installed and ready for the ultrasonic experiment, which is also the image behind me. So how does it work? So literally that experiment, so it's a high pressure experiment where we measure three informations at the same time. One, obviously, is the X-rays diffraction of the sample, which is kind of the classic measurement in the synchrotron. And also, at the same time, we are also measuring the length of the sample by using the X-ray radiography techniques. which I will show more in detail after. And at the same time, we are also measuring the arrival time of some acoustic wave by using a probe which is attached to one's at the backside of one anvil. I will show again later how do we do, but basically having those informations, the length and the travel time of the wave, give you by this very simple relation the speed of a P and S wave in the side of the sample. So the cell assemblies is generally made like this, starting with the transducer, which is a piezoelectric crystal, which is pasted at one face of the tungsten carbide anvil. So we are using a dual mode transducer, which can generate generate a resonant frequency of 60 megahertz for the P wave and 40 megahertz for the S wave. And using this crystal, we are going to generate an acoustic wave, which will travel to the inside of the cell and be reflected at the different interfaces from the surface to more deep inside where the sample is located. So here I show an example of sample that was sintered before the experiment. And yeah, because yes. So here is a more schematic view of the measurement. So like I explained before, the input signal is sent as a pulse. And it will be reflected at each interface of the materials composing the cell. But the echoes so at each reflection, an echo will be emitted and reflected back to the device that serves to measure it, so basically an oscilloscope. And those echoes will be recorded. And the difference of the arrival time between those echoes is what gives you the travel time of the acoustic wave inside of the sample. So to achieve that, certain requirements are necessary for the sample. At first, if we want to measure the sound velocities of one material, we need that sample to be chemically homogeneous, which nowadays is, I guess, well achieved, but it could be problematic because the sample that we are looking at is relatively big, like about 1 or 2 millimeters in diameter. And the length also needs to be about 1 millimeter or something. It's easy to understand because if the sample is too short, you will have those two waves which will be overlap, and therefore it's going to be difficult to analyze the travel time. Another thing is that we need the sample to be well sintered, means no pores, as pores counts also in the speed of the propagation speed of the wave. But that problem is actually maybe less problematic if after you reach a certain pressure, like above 10 or more GPM. And to match with the frequency, the resonant frequency that we are using, we also need a certain requirement on the grain size to avoid the reflection of acoustic wave inside of the sample, inside of the big grains or something. And to maximize the intensity of the reflection, we also need the surface to be mirror polish and parallel. So all of that makes the synthesis of the sample maybe the most important part of the measurement in order to achieve a good measurement. Okay, so aside from that, if we have a good sample, we can proceed to such kind of measurement. So here I show an example of P and S wave acoustic signal at high pressure and high temperature. So like I described before, the signal will first arrive and be reflected at the back of the anvil, then at the back of the buffer and front of the sample, and then at the back of the sample. We do observe the same thing with the S wave, which, as you can see, are a little bit delayed because they are slower than the P waves in general. So here I show a picture of the device we are using. This is just a regular oscilloscope and a waveform generator. So how do we analyze this signal? We are using the pulse echo method, which was first presented by the Stony Brook group, which in this method we overlap the echo of the sample with the echo of the buffer, and derive the time delay to derive the travel time from the delay between the two echoes. So for that, we, Kono et al. Has derived the procedure to analyze this shifting of the echoes by using a cross-correlation function, which can give result for the measurement of the travel time by about 0.2 nanosecond, which is about an uncertainty of 0.1% of the measurement of the travel time. So literally, the travel time measurement is something that we can do quite precisely. So here I show another example of successive measurement, which can be done as a function of increasing pressure, like you can see here, and also as a function of increasing temperature, which as you can see here. And I show this figure because the waves are not so beautiful, actually not very good looking. But what I wanted to show here is that even though the measurement is something that we can do in routine, at high temperature, things become much more complicated. And as you can see, when we approach the temperature of the mantle, the Earth's mantle, it's becoming increasingly difficult to have a signal. So I will show in the later part of my talk how we try to overcome these difficulties. So another measurement that we do to this experiment is to measure the length of the sample. So for that, we recently developed a new setup for the camera and the X-ray radiography, where we place the camera just at the back of the press. It's very close. And we also open a space so that we can take X-ray diffraction in the same position. So that means that there is little to no transition time between imaging and X-ray diffraction acquisition. So the length of the sample is analyzed by determined by analyzing the gray contrast. So here I show an experiment where we use a tungsten carbide buffer and an aluminum foil at the ends of the sample. So here is the gray profile that we get from the X-ray radiography. And by analyzing this distance, we can determine the length of the sample as a function of a temperature and as a function of a pressure, like we did for the travel time. As you probably saw in this slide, the length of the sample is determined in a pixel, which is dependent on the quality of the camera. So in order to calibrate to know the size of each pixel, we are using a method that we call the steel sphere method, where we measure the diameter of a sphere with that we know the diameter, and then we can plot this relation that gives us the real length of each pixel. So at the moment, we are working with a setup that allows to have a pixel size of about 1 micrometer. So all those process, of course, in the past were tedious. We had to do everything one by one, but nowadays we now automated everything, and then we can do the acquisition of both travel time and image almost simultaneously. As you can see, for example, here in this study where we measured continuously the P and S wave velocities as a function of increasing temperature for, I think it was for a metallic glass. And then we can see some detail of the transition of the glass as we increase the temperature. Also, last but not least is the X-ray diffraction. So we, of course, have a solid-state detector at the back of the press. And using this detector, we can take X-ray diffraction of the sample, which can be used later to construct the EOS and have some constraint on the density of the material that we are measuring the sound velocities. So just to give an idea about where we are now, I made this little comparison by year. So when I joined the GRC, we were just publishing the paper for the meteorite and the ringwood height. And if you see here, the x-axis represents the pressure and here represents the temperature. These experiments were close, but still not enough to match with the condition of the mantle geotherm. So that means that in order to apply this result to the implication of the Earth's interior, we needed some extrapolation in terms of pressure and temperature. Of course, these were the best data that we had at the time, so we had to do with it. But in order to fully understand what may happen in the Earth, we need to do those experiments at high pressure and high temperature. Therefore, we have been working to try to develop these experiments to reach such kind of conditions, as well as other groups in the world. So after several years, there were some progress or not. MGO were measured a little bit higher temperature, but pressure was lower. And then we started to do some measurements at relatively higher temperature, higher pressure. Also, the APS group had this experiment on the bridgemanite at about 25 GPa. And finally, in 2016, we were able to do the first measurement at about 2000 Kelvin on the meteorite sample, which were followed by other experiments at slightly higher pressure on the meteorite. But I must say that those experiments were kind of like miracles. That means that even though, as you can see, we did many more experiments on different materials, we could not make this setup a routine experiment. And yeah. But recently, we also made a different, we adopted different strategy, which I will show a little bit later for the bridgemanite, what we are doing. And also for the alloys, where we wanted to measure the velocities of the fully molten FeNiS alloys. So we developed some cell which can provide such high pressure, high temperature, while measuring the sound velocities, means that all the measurement that I presented just. So, well, that being said, I want to now just present a little bit of what have been done before and published before, and how was it applied to discuss the Earth's interior. So, like I showed in my the previous section, when I arrived at GRC, those two studies were just published. One was about the pyrolytic meteorite, published by Erifune in 2008, and another one for the ringwoodite, published by Higo et al. And what was interesting with those studies is that for the first time, they measured the sound velocities of those two important mantle minerals at conditions which were comparable to those of the mantle. And using those elasticity data, they reconstructed the sound velocity profiles of pyrolytic rock at the depths of about 500 kilometers. And what they concluded is that these velocities matched well with the seismic profile. So at that time, I think that because we need to put things back in context. I mean, in 2008, I thought that those papers were really remarkable because they really connected the result in the lab directly to natural observations. Of course, it was not perfect. I mean, and we understand that now, that this explanation is only valid for certain depths. But when you look at a little bit deeper in the mantle transition zone, you see that the velocities are too low. And it's because also those models are very precise. They become like impossible to reconcile with the seismic observation because the error bars provided by those techniques are small. So therefore, there is no doubt that they cannot represent the bottom part of the mantle transition zone. So later, when I joined the GRC, we had this idea that maybe the difference could be provided by the crystallization of the calcium perovskite, now called Dave-Maurit. And we did measure the sound velocities of the calcium perovskite and recalculated those models. But we found that the calcium perovskite actually, the increment of the velocities by this phase are insufficient to explain the high velocities observed at the bottom of the mantle transition region, particularly for the VS. Since this phase is also a component of the MORB, we propose that maybe the MORB could be an explanation, but again, the velocities are too low to match with the seismic models, and which led us to the conclusion that only Aspergite composition can explain the high velocities of the bottom part of the mantle transition zone. So actually, it was new result at the time, but this idea is not new. Actually, already Ringwood in the 90s, late 80s and 90s, already imagined that we had such kind of a situation where the slab would accumulate above the 660 and having some ultramafic component laying down above the 660. But we were happy that our results could provide maybe some evidence that this was true. So using our data, we tried to derive some model of the slab distribution around the 660, where Aspergite layer would become the main part of the stagnant slab, and where the basaltic component, which are denser, would go to the lower mantle. So this view is actually quite consistent and find some evidence in observation of the slab stagnation in between 660 and 1,000 kilometers. Also some finding of diamond inclusion recently, and particularly the studies that led to the name of the calcium perovskite, to Dave-Maurit. Those studies also suggest that maybe the basalt go to the lower mantle, preferably. However, there were also other point of view. And there is the study by on the hydrous phases, by, for example, the work of Marta Pamato and Brandon Schmant, who instead sees that this seismic perturbation beneath the 660 may be caused by dehydration melting. And also some work on the water-bearing water ability of the bridgemanite, the bridgeman ability to absorb water went against our idea. It's also worth mentioning that there is also an increasing number of geodynamic simulation that prefer the accumulation of the basalt in the mantle transition zone. And while, of course, they do have argument based on their initial constraint, it's and the subduction, I mean the subduction mode of the slab. This result goes against the result from our experiment and also from the the result of the mineral physics in general. So in order to try to understand, to try to reconcile of all this existing problem, we try to reimagine, not reimagine, but try to understand what are we doing when we calculate the velocity of the rock. So generally what we do is we average the elasticity of the component of the rock using this Voigt, Russ, and Hill average, which just I wrote the equations here. So this average assume that the minerals in the void band are under constant strain condition, while in the Russ band they are under constant stress condition. And as you can see, this strongly depends on the texture of the rock. However, many petrological studies in the past have shown that rock texture is not something that follow a clear pattern like that. As you can see here, some experiment on the pyrolites shows such kind of well-equilibrated texture where aspergite is kind of similar, but when you look at some basalt, you have a much different texture. So the question is there, are those models capable, even if we know perfectly the elasticity of all the minerals, are those models capable of reproducing well the sound velocity of the rock? So there is little to no study on the subject, especially at high pressure, except for this work from the Stony Brook group in 2015, where they measured the velocity of, I think it's a KLB1 peridotite, which they compare to the average. And here is the result, literally. So they found that their average is within uncertainty in a good agreement with the experimental data. However, as you can see, the uncertainty is large. And those data were only taken at a room temperature. And therefore, in order to understand if these models can be applied for the mantle, we need to carry out such kind of experiment at high pressure and high temperature. So this is literally what we did at the GRC. So first we started with the pyrolite system, and using the presses at our facilities, we synthesized samples of pyrolite at different pressure. So for the synthesis, we use reacted oxides that we put directly in a rhenium capsule and compressed at pressure in between 8 and 18 GPa in the two presses that you see here on the picture. So here I show an example of sample. This one is a wasdelite plus mesorite, which was synthesized at 16 GPa and 2000 Kelvin. So here I show this is an analysis of the texture of the sample, as you can see, and as it is expected, depending on the phase constituting the sample, we do observe different textures. We did analyze the composition, which is very consistent with previous studies on the pyrolite system. And so in the end, so in summary, the samples that we made represent both the chemical variation of the mantle, pyrolytic mantle, as a function of pressure and temperature, and also the mineralogical composition of the pyrolytic mantle. So using those samples, we carried out ultrasonic experiments, and here I will show the result. I show here the result in terms of the Vs over Vp, and compare the results to the peridotite experiment of Wang et al., and also a model of the pyrolite calculated using the elasticity of the minerals taken independently. So here are the experiments carried out at 8 GPa. And as you can see in the lower pressure range, the experimental data are not, how can I say, not inconsistent with the calculated model. At least the difference looks to be very small. However, when we increase the pressure, it means that when we start to form, when the pyroxene disappeared and start to form more majoritic garnet, and the transition to wasellite, we can see that the data starts to be very different from the calculated model. So using those data, we calculated the pressure and the temperature dependence of the velocities in those rock assemblages. Here I just show the final result. And from that, we can derive some model of the velocities of the pyrolytic rock at a certain depth. Okay, the thing I didn't say, I'm sorry, I'm going to say it now, is that the measurements were carried out around the pressure and temperature where the sample was synthesized, so that we avoid any additional reaction and transformation of the sample during the ultrasonic measurement. So using those data, we can express the, let's say, real velocity of the mantle at the depths where the sample was synthesized. So as we can see, using those models, the olivine plus pyroxene plus garnet samples match quite well with the seismic models. We see, however, that when the sample is made of wasellite and majoritic garnet, we start to see some increasing of the discrepancies. So two reasons can be, we can find two reasons for that. One is, of course, like I just explained at the beginning of this section, the velocities of the bulk velocities of the rock are not equal of the average of the velocities of the minerals taken independently. Another possibility, of course, is that the elasticity data that we use are not accurate. That is especially true for data at pressure above 12 or 15 GPa, where my data are still scarce. For example, I just take an example to understand wasellite data that we use for the models are data taken several years ago below 12 GPa, where wasellite is not stable. So they are metastable data. So those data were extrapolated to high pressure and high temperature. So that could be one of the causes for the discrepancy and the different slope that we observe. Anyway, using our new data, we can calculate the velocity jump at the 410. And as you can see here, when the pyroxene have not dissolved completely in the pyrolite, we found a velocity jump which is about 4% for the P wave and about 6% for the S wave. So this velocity jump is still larger than the global seismic model, but much smaller than the velocities calculated using the VRH average. We also calculated the velocity jump, which would be caused if the transition at the 410 was correlated with the disappearance of the pyroxene. And we found that the velocity jump would be higher, which means that it's unlikely that pyroxene completely disappear at 400 kilometers. Okay, so pyrrolite is not the only composition expected in the mantle transition zone. Like I said, several recent studies propose that basalt may accumulate. So we also did the same thing with basalt composition. We synthesize samples at different pressure and temperature, which represent the transformation of the basalt composition as a function of increasing depth. So here I just show a picture of the sample. They do not look really beautiful, but actually they are well sintered and they can be polished a mirror surface and parallel. So we see that just for the record that the increase of the orange color, which is related to the increase of the garnet content, and surprisingly, sample turned completely black after passing into the lower mantle. So here I show also the result. So these are for the data at 300 Kelvin only at the moment. We do have the data at high temperature, but I'm still working on that, so I cannot show the result today. But we can see already that the sound velocity that we measure on the rock samples at low pressure are close to the VRH model. VRH model which are calculated based on the equilibrium experiments. So some discrepancy may exist due to the phase proportions. But generally speaking, and I tried also to change the proportions here, the difference is not so large. At higher pressure, however, we can see that the discrepancies increase again. So, like I said, for the pyrrolite, this could be related to two things, whether that the texture of the rocks change, and therefore the average become, the model for the average, it become not applicable, or the materials that constitute the rocks, the elasticity of those materials are not well constrained. And so we took the data at to high pressure. So here I did a corrected VRH average, where I use actually the proportion of the minerals in our model, in our sample, sorry, and plotted it against so we can see, as you can see here, the difference is even larger, which suggests that there may be something wrong in the constraint on the elasticity of the minerals, particularly the stishovite. I think it's not very well constrained in this pressure and temperature range. So here I show in this figure a comparison of the VS over VP for the the pyrrolite in green and basalt in blue. Yes, and also this experiment. So basically, from this set of data, what we understand is that the lower velocities of pyrrolite above 410 could be reconciled by a small chemical change, such as, for example, an increase of iron in olivine, likely olivine, garnet or pyroxene, maybe not, or temperature variation. But the velocity jump across the 410 that we measured by the velocities of the rock aggregates is smaller than what is expected from an average approach, which lower the requirements for other process, such as partial melting or the presence of water in that region. Also, the presence of basalt above the 660 cannot explain the high seismic shear velocity, which is in agreement with our previous studies using averages. And again, it suggests that only icebergite has velocity which is high enough to explain the high velocity profile in those regions. Okay, so now that we tested the rock models, there is one thing that we need to also test to be sure that our considerations are correct. And it is the effect of the partial melting on the sound velocities of those mantle rock. So literally, so here I show a schematic representation of our experimental setup where you have the transducer, which send the input signal in the buffer and the sample. So in the ideal case, when the sample is made of one material and with homogeneous grain size, we do get ideal echoes which are well separated and with little to no attenuation in the signal. On the other hand, when the medium becomes heterogeneous, the travel time is delayed. And we also do observe some wave attenuation. So this process should permit to identify should be related to the nature of the heterogeneity. So in order to test this assumption, so we carried out such experiment. But before presenting what we did, I would like to mention that there were some previous studies which was carried out by Chantel et al. They measured the velocities of olivine plus morve aggregate, and they found that the basalt, when melted, is going in the grain boundaries of the olivine rock aggregate and causes large drop of velocities. But the pressure of this experiment is quite low. It's about 2 GPa, which is quite far from the pressures of the mantle transition zone. Also, the measurement to be put a little bit of criticism. The data looks a little bit strange because adding morve to olivine almost does not change the velocity when the sample is not molten, but then suddenly decrease the velocities by a few percent when it's even slightly molten. So in order to prove or disprove this result, we also carried out our own partial melting experiment. So first, in order to understand how does the melting affect the properties of the sound velocities, we carried out an experiment with a simple system, which is olivine plus FES. And we measured so the sound velocity upon partial melting of FES for samples with different FES content. And what we found is that when the FES melt, we do observe a drop in the velocities. But as you can see, the drop of the velocity is much less obvious than what reported by the previous studies. So we also analyzed the texture of the sample and found that the melting process of the FES in this olivine sample is mostly driven by the melt pockets mechanism, where the melt will form pockets at the triple junction of the olivine grains. But when we carried out the same experiment using wazelite and FES, so here is just some detail of the experiment where we see that at the beginning, some olivine were still in the sample, unfortunately. But by heating the sample long enough at high pressure, we completely transform the sample to Wazelite and then melted the FES and then measured the sound velocities during that process. So we see that when we do that in the Wazelite plus FES system, we have a much larger drop of the velocities. Just I want to precise, this is the travel time. So this is the inverse of the velocity. But basically, we do observe very rapid and large drop of the velocities when we do the experiment in the Wazelite system. This experiment suggests that not only the amount of melt and the composition of the melt, but also the silicate matrix that constrains the melt, is of primary importance to understand how much the velocities will drop upon the partial melting. So here is another, so this was published, I think last year in PSL. So we found that the FES melt have a substantial effect on the sound velocities of olivine aggregates, but in proportion less than what was reported for the olivine plus basalt. The effect seems to be more pronounced than theoretical predictions, and we found that it depends a lot on the geometry and size of the melt heterogeneity, which could explain why the experiment carried out with Wazelite, and we also have data on ringwoodite plus FES, suggests that the nature of the silicate matrix and grain boundaries effect is also significant and needs to be studied. So before finishing my talk, I would like just to mention that the facilities and that I presented in this presentation are available to joint use research by the previous program. So we do have several presses, including the Beauchamp, which is directly related to force, because this is literally the older brother of the press Ichiban, which has been installed. And using those apparatus, we are using them mostly for the sample synthesis. We do have some accompanying facilities, such as high temperature furnace and laser levitation furnace, which can be used to prepare samples and then load directly in the cell to carry out high pressure experiments. So here I show just a little sample of a little view of the sample that we synthesize, and which those samples, I mean, the quality of the sample is absolutely necessary to carry out such a delicate measurement at high pressure and high temperature. And I believe that in the future, force will be able also to synthesize such high quality samples, which can be applied not only for the ultrasonic measurement, of course, but also, for the diamond orbit cell and laser shock experiment, for example, in the case of very highly transparent samples. And that's the end of my talk. Thank you for your attention.
Thank you, Dr. Greaux. It's a great talk. The samples are gorgeous. Amazing to see those. And
Thank
again,
you.
if you have questions for Dr. Greaux, you can type them in the chat and we'll read them out, or you can raise your hand. Sibo, would you like to ask your question?
Oh, hey, can you hear me?
Yep.
Yes, I can hear you.
Oh, hey, this is Steeve from Arizona State University. So I actually have a question about the sound velocity of the rocks at high pressure.
Mhm.
So you see the direct the measurement of those rocks are even higher than the VRH average. So I was wondering because I thought there is a gold layer between your sample and backing material.
Mhm.
Is that gonna affect your measurement? If
Mhm.
is there any correction you did on that layer?
Yeah, so the correction, of course, we do have some procedure to correct the, try to find my slide. Yes, we do have a procedure to correct the effect of the bond. But frankly speaking, okay, so there is many. Yes, you're talking about this bond. Yeah.
Yeah.
So there is many different views on this bond, and of course there is Ian Jackson made some proposed some model to make a correction for the effect of this bond. The thing is that, and I think this is has been ignored in those models. The thickness of the bond will change at high pressure, and particularly at very high pressure, to the point that the reflection in the bond will become negligible at high pressure. I didn't show today, but we are working now with some mathematicians to re-express these models, because all the models so far at the moment do not take into account the fact that the bond thickness decreases also with pressure and temperature. So to answer your question,
Okay,
yes.
so you
Correction.
you
Yeah.
actually
Sorry.
sorry, I have a bad internet here. So I'm at a beam line. Sorry. So you do see evidence that those gold are the thickness of those gold are gonna lower under the high pressure. So do you have any direct images to show that one?
Yeah, of course. I don't know if you see it. But we do, of course, it's we are talking about the 2.5 microns decrease to something. So I believe that, yeah, probably the thickness of the bond cannot be measured, but we need to assume a model for the reduction of this bond. Yeah. But I'm a little bit also surprised by there's another question. I'm a little bit surprised by your question, because I think that even in the case where the bond, the correction is applied, generally this correction is not large. It's within a few nanoseconds. So I don't believe that this will change drastically the measurement of the sound velocity. Of course, there might be a small difference, but not of the scale that can explain the difference between the VRH average and the measurement on the rock velocity, in my opinion. Well, I don't know, what do you think about that?
Oh yeah, because I recently read a paper. Yeah, they just by correcting the data, they changed the velocity by like 5%. So yeah, that's my concern.
You're probably talking about the NODA paper, right?
Yes, 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 that one.
Okay, I know that paper, but the problem with that paper is that they are using a theoretical calculation for the gold, where the VS they calculate is 20% lower than any experimental data. So I think first, this is a problem. And the second, they do not consider uh, the reduction of their bond thickness is fixed to 2.5 micrometer. So I think also this is why they have such a large correction in the paper.
I see, I see. Yeah, thank you, thank you. Yeah,
No problem.
thank you. That's a
Okay.
good thought. Thank you.
Thanks, Sibo. All right, Matt, you can go ahead and ask your question.
Okay, I had the thing to unmute. Hey, Steve, it's Matt. How are you?
Hey, Matt. Hey, how are you doing? Long time no see.
Yeah, how are you doing?
Yeah, fine, fine. I'm
That's
here.
good to hear. I was
Yeah.
just going to actually kind of back you up on the bond distance thing. If you forward calculate it, anything less than about 2.3 microns disappears in the noise to the point where it doesn't change the statistical significance of the final decimal point of the travel time measurement. So, and that if you're starting with a 2.5 micron foil, by the time you get up above about 2 GPa, it becomes negligible. So I don't think it affects the model results that you're getting from your data. Hopefully, it should be fine. I was just backing up on that.
Okay, thank you for a comment. Yeah, this is some discussion I also had several years ago with Ian Jackson, and he also said that he believes that above 15 GPa, you don't need to even the one foil correction, you don't need to do it.
Right. Yep, totally agreed. Good to see you.
Yeah, it's good to hear you. Yeah.
Sibo, did you have a follow-up before we move on to Dave Walker?
Oh, sorry, I don't have any questions. Yeah, I just
Oh,
don't
okay.
think about it. Thank you.
Yeah. Okay, go ahead, David Walker.
I cannot hear anything.
My question is, do you have a physical theory for why the signal fades at high temperature? Or are you just exploring technical issues that might be responsible for the loss of signal at high temperature?
Yeah. So in this particular experiment, we found so we went to 2000 Kelvin and the signal completely disappeared. And then after we quenched, the signal reappeared. And when we opened the cell, we found out that the buffer was broken. I mean, it has a large crack right in the middle. So it may be one of the cause, but not all, I think. I think that the gradual reduction of the signal is also caused by the epoxy between the transducer and the anvil, which expand with temperature and push the transducer further from the surface of the anvil. So that's why the signal becomes weaker. But the complete extinction is something different. And of course, as you saw in my last slide here, the anvil takes quite some damage from this experiment. I mean, like, of course, that is blow out during decompression, but also the piston. We are using a alumina piston. Even though it's softer than the tungsten carbide anvil, the surface is smaller. That means it push back also the anvil, and it causes a depression at the surface of the anvil. So I think all those factors come into play, and you see the signal disappearing and sometimes reappearing. Depends on how those deformation things work together. So that's why sometimes we have, like I said, miracle experiment. I don't know how it happened. We just measured like a superb data at very high temperature, but mostly, yeah, those experiments fail when we try to increase temperature. So just to, yeah, so we don't have a clear explanation, but we are trying to solve it by a try and error method, by putting some support frame or cooling the anvils or stuff like that. So sometimes it works, sometimes not.
Yeah.
We still need to do more experiments to probably define a clear procedure to make a safe experiment under those conditions.
Thanks. So I interpret your answer as you're not looking for new physics here. You're looking to
I see what. Okay, so
tie up the loose ends in the technical execution.
I think it's more technical than physical. Yeah.
Thank you.
Welcome.
Okay, go ahead, Kisei.
Oh yeah, thanks, Steve. So in my last part of your talk, you showed the sound velocity measurement of the Wasserite Morgan mixture.
Yeah.
And maybe that you did some experiments maybe last week, right? Then there might
Yes.
not be the answer, but that
Mm.
like it looks like a melting point is quite low if this is
Yes.
true. So
Yes.
of course, yeah, melting point of the Wasserite is relatively high, and the morgue also relatively high. And I'm curious, like so melting is determined based on the disappearance of the S wave, right? So
Not only, we also monitor the X-ray diffraction.
oh yeah, I see. And from the background, right?
Yes, yes, you can see here I put in the yellow. We know that like when it's met, you have this increase of background and up
Yeah,
to 70. Yeah, so we monitor that, and you can also see that the peaks disappear. And so this 1600 degrees C, I think that's the basaltic melt started to react with the wasdelite, which, as you can see, wasdelite peaks start to become smaller. We have appearance of new peaks. I don't know what it is. I still need to analyze the recovered sample. But no, we check also by the XRD. And to answer your point, there is a paper by the Yang Hao Lin recently in the Nature Geoscience. He showed that actually the melting temperature is strongly dependent of the oxygen fugacity of the truth is that uh, when you said, and you are right, that the temperature is low, this is based on the knowledge of from experiment realized in the metallic capsule. So generally more relatively reducing environment. But our experiment, the sample is placed in the MgO sleeve. So that means we are more oxidizing than those experiments. So actually, this is also surprising to me that it melts at so low temperature, but that's what we observe. And I believe that maybe that's due to the oxygen fugacity of the cell itself. It's
Maybe accordingly, maybe the difference of the maybe ferric ferrous ion ratio in the minerals, or
uh, it's a good question, but it's I would say because if you melt, a ferric ion likes the melt.
right,
So, so the mineral should stay ferrous
right.
and having all the ferric ion in the melt. I don't know how does it play for the oxygen mobility in the whole sample, but uh, I believe this all of this goes in the direction of melting at lower temperature than what is expected in a more reducing environment.
Yeah, maybe later maybe you might maybe analyze using the EPMA or something, and you can get the phase composition, and you can maybe guess like a melting reaction or something, and that might be
Yeah,
the
yeah.
clue.
I plan to conduct actually additional experiment for this experiment. I want to verify, but I'm quite confident that you probably saw the Young House paper. And I think that when they did the experiment at the same composition as the previous work and high oxygen fugacity, they do observe actually melting temperature at a much lower temperature than what was reported before. So that might be something related, I think.
Yeah, maybe then probably the result is not the like a technical problem, but maybe chemistry is more important.
Yeah.
If your
Of,
result
of
is
course, of course, I understand the concern also related to that one is that how well does this experiment models what may happen inside of the Earth? But oxygen fugacity of the Earth is also something that is still under discussion. So
yeah. Oh, okay. Yeah. Thank you, Steve. Yeah.
no problem.
Yeah. Thank you again, Steve, and thank you for everyone for tuning in. We appreciate it. We'll see you next time.
Yeah, thank you for the invitation. Yeah.
Yeah, thank you, Steve. Yeah.